Welcome to our lessons on partial differential equations. We start a new topic in this series of videos. In this series of videos, we're going to take a look at Fourier series, and we intend to take a look at periodic functions. But in 1807, the French mathematician and physicist by the name Joseph Fourier submitted a paper on heat conduction to the Academy of Sciences. And in that paper, he made a claim that any function can be expanded in the form of an infinite sum of trigonometric function. That is, any function can be written in this form. Now, using the summation notation, we can say this f of x is approximately equal to a naught over 2 plus summation from m equals 1 to infinity am cos mx plus bm sin mx. So that's Fourier's assertion. But before we look at the computation of Fourier series, let's take a look at some key functions which comes along with the Fourier series and its application. So we are going to take a look at periodic functions. We will look at symmetric functions, even and odd functions. We're also going to look at orthogonality relations of these functions and other functions. So let's start with the periodic functions. A function f of x is defined for the interval negative infinity to positive infinity is called periodic if there is a certain number p greater than 0 such that f of x plus p is always equal to f of x for all x in the domain. So no matter the value of x, when you add p to x, it will still give you the same thing. That is, if f is periodic with period p, then f of x plus p is equal to f of x. If you add another p to make it 2p, that's f of x plus p is the same thing, so come back give you the same f of x. No matter how many times you add a p, it's going to give you the same thing. So in general, you're saying that if f of x is periodic with period p, then f of x plus np equals f of x, where n belongs to the set of integers. So no matter the number of integer multiples p that you add, the function will also give you the same thing. And the smallest number p for which this is true is what we call a period. So this number p, the smallest among them, is what we call a period. Examples of periodic functions are the trigonometric function, that's sine, cosine, tangent, secant, cosecant, cotangent, and then cotangent functions. So for example, sine pi on 6 is 1 over 2. If you add 2 pi to pi on 6 and you find the sine, you still have. If you add 4 pi, that is 2 times 2 pi, you still have. If you add 3 times of 2 pi, you get half. So we can say that sine has a period of 2 pi. So every 2 pi, it repeats itself. So let's look at this diagram. This is the sine curve. And you can see from here to here, the graph repeats again. It repeats up and coming down here and coming repeats again. To every 2 pi, the cycle is complete and it repeats the cycle begin again. So we are saying that sine has a period of 2 pi. Similarly for cos, pi on 4 is root 2 on 2. If you add 2 pi to cos pi on 4, you get the same thing. If you add 2 times 2 pi to it, you get the same thing. So we also say that cosine is periodic and have a period of 2 pi. And if I do the sketch, you can see the same thing. Here is x equal to 0, here is x equal to 2 pi, and it repeats again to x equals to 4 pi. So cosine 2 has a period of 2 pi. Tangent, tan pi on 4 is 1. And you add pi to pi on 4, you get the same one. If you add 2 pi, you get the same one. If you add 3 pi, you get the same one. So you can see that tangent has a period of pi. And if you pick the graph, you can see that from here to here, it repeats itself. From here to here, it repeats itself. So tangent has a period of pi. Cotangent similarly has a period of pi. So you can see pi, cotangent, pi on 4, they are all the same thing. So it also has a period of pi. Now one thing you to take note is that since sine and cosine are periodic with 2 pi, they are reciprocal as cosine and secant, which are reciprocal sine and cosine, are also periodic with period 2 pi. The same manner, similarly, reciprocal of tangent is cotangent. So cotangent 2 has a period of pi. So this is a graph of cotangent, and you see that they are repeating themselves. This is a graph of sec, and you can see that every 2 pi, the thing repeats itself, the same repetition here, both up and down. Then cosec, you can see that after 2 pi here, what is here begin the repetition again and continues like that. Now let's consider the following functions: sine 2x, sine 4x, sine ax. We want to find the period of the function, but we are going to use graphical method. So let's go to GeoGebra and come back. Okay, so let's look at sine x. If you plot a graph of sine x, the period is 2 pi. So you can see that it's 2 pi here. Now if you plot sine 2x, the period now reduces to pi. Consider the complete cycle come back to pi. So when the sine x is 2 pi, when it's sine 2x, the period is pi. So let's link the relationship between the number here and then the period. So when it's sine 4x, the period was pi on 2. You can check from here. And finally, when it's pi sine 4x, 8x, when it's sine 8x, the period is pi on 4. So we have to record this. Sine 8x, the period is pi on 4. 4x, the period is pi on 2. See here? 2x, the period is pi. And then sine x, the period is 2 pi. So let's use this one to check the period, how to get a period of this function. Okay, well, come back. You realize that in the GeoGebra, the period of sine x, 2 pi. Then we realize that the period of sine 2x was pi. And we know this period of sine x is 2 pi, so the pi is the same as 2 pi over 2. And then we also saw that the period of sine 4x was pi on 2, and it is the same as this 2 pi over 4. And the period of sine 8x was pi on 4, which is the same as 2 pi over 8. So these 2, this 4, this 8 are the coefficients here. And the 2 pi is the period of sine. So this generalizes that is for sine of nx, the period 2 pi over n. So that's the generalization here. So it's the same way for cos nx, the period will be 2 pi over n. For tan nx, since the period of tan is pi, it will be pi over n. And so let's use this idea to look at the period of the following. So the period of tan 5x, we know the period of tan is pi, so we divide by the n, which is 5. So that's the period. Now this one is pi on 3x. The period of sine is 2 pi, and the coefficient of sine here is pi on 3, which is going to give us 6 pi over 3. Sorry, over pi. And pi over pi cancel, we're going to get 6. So the period is 6. Here the period is 2 pi over 7. It's also 2 pi because it's the reciprocal of cosine. So it becomes 2 pi over 6 pi over 5. That's our n. So that's going to give us 10 pi over 6 pi. The pi will cancel the pi. That's going to give us 5 over 3. So this is the period of 6 pi on 5x. Let's consider the following functions. I have f of x equals sine x plus 4 cos x. G of x equals sine 4x plus cos 8x plus tan 2x. We want to plot these two functions. This is the first one, f of x equals sine x plus cos 4x. And the period for this function is 2 pi. If you check the nature of the curve up to this part, the period is 2 pi because it will start beginning repeating itself. Now if you check this function too, you have sine 4x plus cos 8x plus tan 2x. The period is pi on 2. Because from here to here it repeats itself again. So the period is pi on 2. Now what can we see? We can see that in each of the cases, this is the period of this is 2 pi. The period of this pi over 2, the individual function. But the period of the whole function becomes this. If you go again, period of this function here is pi on 2. Period of this is pi on 4. Period of this is pi on 2. So the biggest now is pi on 2. So the period of this function is pi on 2. That tells you that if you have sums of function, the period of the largest of the period of individual function gives you the period of function. So for example, if you have f of x equals to this, we have this one being 2 pi, this one being 2 pi, this one being pi. The period will be 2 pi. If you pick this, the period of this one is 2 pi over 3. The period of this one is 2 pi over 5. And then the biggest among them is this. So that will be the period of the function. These are some few trials for you. You can try your hands on them. Now let's go to polynomial functions. So let's look at this function. First function that I want to look at is a function f of x equal to 3 plus cos x. Now you can see that what the 3 here does is to raise this function to the top and it's still repeating. So this function here is periodic and has a period of 2 pi. But let's look for another function. Take away this and look for the function g of x equals x plus sine x. If you plot this curve, you realize that this curve keeps on going up as x changes over there. So this function never repeats itself. So we are saying that this function is not periodic, and this is a sum of a polynomial and a trigonometric function. The first one is a constant. Let's now look at another function. We are going to look at a fully polynomial function, a linear function here. So that is a function 2x plus 1. You can see that this function is straight line going up, it does not repeat itself again. So it is also non-periodic. And the last but not the least, let's consider the function x squared plus 2x minus 1. If you plot it, you have the shape, and you can see that it does not repeat itself as you move along. So we say all these functions are periodic, but the one here, which is the f of x equals to 3 plus cos x, we realize that that one was periodic because the cosine is periodic, and the 3 here raised the whole thing by just 3. So we say this function is periodic. Thank you for watching. We meet again.